Hi, so we're going to be talking about desulfurization in industrial processes. So as the name suggests, desulfurization is simply the removal of sulfur from a material. So first we're going to be going over some background of why we even need to remove this sulfur in the first place. So sulfur compounds such as sulfur dioxide and hydrogen sulfide are often produced during industrial processes. These can range from pulp and paper processing, rayon manufacturing, electricity generation, metal processing, and industrial boiling. However, the main source of this production that we're going to be talking about today is through oil and gas refining. So shown on the side is a process flow chart of a typical refining process. Just to review, refining is the conversion of crude oil into practical products such as gasoline and other hydrocarbon fuels. As you can see, there's a lot going on in this chart, but the main steps are distilling, cracking, reforming, treating, and blending. The main step of interest to us, though, is treating. So during this process, the naturally occurring sulfur that exists in this crude oil is treated in order to eliminate the sulfur content from the crude oil. So a common way of doing this is through hydrotreating, which results in hydrogen sulfide. So other treatments can also be used that result in sulfur dioxide too. But on this chart specifically, the main part where the side product is leaving is the off-gas portion in the top right. So this is shown by the hydrogen sulfide entering the Klaus sulfur plant, where this hydrogen sulfide was extracted using amine treating. So why do we care about these chemicals in the first place? Because if they're not harmful to us, we could just release them into the atmosphere and everything would be fine. But in actuality, they're both extremely toxic to humans, so we want to prevent these byproducts from contaminating our environment. So here are the chemical hazard warnings for these chemicals. As you can see, hydrogen sulfide is extremely flammable as it's ranked a 4, and both compounds are extremely toxic to humans as they are ranked 4 and 3 respectively, where 4 is, just for reference, the highest something can be. As such, it's extremely important to convert these byproducts into something else following the treating process in refining and other industrial processes. So here's a proposed reaction. This is one of many that can be utilized to prevent the buildup of these toxic gases in processes that produce this, such as refineries. So this leads us to an example problem to help us further understand how thermodynamics relates to this process in the first place. So this is problem 9.30 in the textbook. And basically, the whole problem statement is we are given the reaction that was just shown on the previous page, and we're told that we need to remove this hydrogen sulfide and sulfur dioxide from an industrial stack, as often done during refinery operations and other industrial processes. So we're given the reaction, as previously mentioned, an equation of state for the two gases. We're told to use the steam tables for water, and we're given a simplification for finding the change in enthalpy at 500 degrees Celsius. We're also given all of the necessary variables to solve this process.
Moving into our problem solution, part A of the problem asks us to find expressions for the fugacity coefficients of both hydrogen sulfide and sulfur dioxide as pure species as a function of pressure. So the virial equation of state given in the problem statement was first rearranged to isolate the volume term as shown here. Fugacity was then found by using this equation and integrating over pressure. Rearranging and simplifying, the fugacity coefficient for each term was found to be e to the b prime xp, where those b prime values are given in the problem statement as shown here. Part B then asks us to calculate the equilibrium constant K at the given temperature of 500 degrees Celsius. This can be done by using the Van 't Hoff equation. So in order to find first the equilibrium constant at standard 298 Kelvin, the standard Gibbs free energy of the reaction was found by summing the Gibbs free energies of formation of each species as shown here. Then the equation delta G equals negative RT ln K was used to find K298, or the equilibrium constant, at 298 Kelvin. The standard enthalpy of reaction was found in the same way by summing all of the enthalpies of formation And the provided equation, shown here, was used to correct for variation with temperature. So substituting in all of the values, the equilibrium constant at 500 degrees Celsius was found to be equal to 0.824. Part C asked us to consider a 3-to-1 feed of only hydrogen sulfide and sulfur dioxide, and to determine the equilibrium conversion at 10 megapascals. So first, the expressions for the mole fraction of each species were written in terms of xi using nu, which is derived from the stoichiometric coefficients from the equation, and then n naught v, which is the initial vapor amount of each species. The equilibrium constant was then written as the product of each species' fugacity to the power of nu, and this was then simplified using the pure species fugacity coefficients, which we calculated in part A, as well as the fugacity coefficient for water, which was found using the steam tables as shown here. And solving and substituting all of those values, xi was found to equal 0.915, or a 91.5% conversion. The remaining parts of this problem then discussed altering the conversion rate. So for part D, if a higher conversion were desired, the pressure would be increased in order to promote greater molecular interactions. For part E, the pressure needed for 95% conversion was calculated to be 221 bar, or 22.1 megapascals, by simply plugging that value, xi equals 0.95, into the equation that we had in part C, and then solving for pressure. For part F, this is an exothermic reaction, so therefore it would be best to lower the temperature as much as possible to maximize conversion. However, in a real reactor, it would be better to change pressure and keep the temperature high for kinetic reasons. And finally, for part G, the addition of inerts to this reaction would decrease the conversion rate because inert molecules would prevent collisions and consequently reactions between the reactant molecules.
So I'm going to talk about some of the practical application of desulfurization and how it is being implemented. So first, let's talk about one method, the sulfur recovery. Sulfur recovery indicates the conversion of hydrogen sulfide to elemental sulfur. The recovery percentage can range from 95 to 99.9% of H2S feed stream, depending on the level of control employed. And one of the common ways is through the Claus process. So the figure here shows a quite typical process flow of Claus sulfur recovery unit. The acid gas on the left side, along with the overhead gases, and a small amount of the recycle from the tail gas unit are burned in the Claus furnace with air to produce a gas mixture of hydrogen sulfide to sulfide dioxide in order to convert to sulfur and water, which is written in the equation above. About 2/3 of the total sulfur recovered is thermally flown directly in the furnace. And as the hot furnace exhaust is cooled in the waste heat boiler, the gaseous sulfur is condensed and removed. Since the reaction is an exothermic process, the removal of the sulfur from the right sides of the reaction provides the driving force for further conversion in the downstream catalytic reactor stages at increasingly low temperature, which favors more conversion to sulfur. The gases are reheated and enter the first catalytic reactor, followed by cooling, sulfur condensation, and removal of sulfur, then repeat again for more recovery. Reaction heat produced in the burner is recovered in the waste heat boiler by generating medium pressure steam that is used in reheating for catalytic stages, and the sulfur products are cooled and condensed, which generates a low pressure stream. The condensed sulfur product is stored in an underground molten sulfur pit, where it is later pumped to truck loading for shipment. Claus tail gas from the last stage sulfur condenser is sent to a tail gas treatment unit to remove the unconverted SO2 before disposal. So the recycling of the sulfur can be used in many other ways. One of the most common ways is to make and use of sulfuric acid, which then can be made into fertilizers, lead acid batteries, and other products relating to inorganic chemicals, magic explosive and glasses, etc. So just a bit about desulfurization, it is a quite important process that helps solve the problem of industrial byproducts and waste that are harmful to the environment. And by utilizing and recycling these byproducts into other products, it's a great way to turn sulfur emission into commercial opportunities. Chemical engineers have a critical role in this desulfurizing process. They can optimize processes by designing and developing new catalysts and absorbent, as well as improving existing methods to increase efficiency, reduce costs, and improve the environmental impact of the process, which is essential for reducing air pollution and meeting environmental regulations.